This week we are talking about divisibility and congruence, modular arithmetic, prime numbers, the concepts of GCD and LCM and how to find them. And then we'll talk about Bezout's identity, Chinese remainder theorem and Fermat's Little theorem. And finally, we will see an application of all of these in cryptography. To begin with, we are going to define divisibility between two integers. We have used this notation before, if you remember, but here is the uh, rigorous definition for integers a, b, c. When we say a divides b, this means there exists an integer c such that a times c equals b. Remember, these are all integers, so essentially what we are saying when a divides b is, well, b is an integer multiple of a. Based on this definition, we have this theorem. This is quite useful in a lot of cases, and it's quite trivial. I'm not going to give the proof because just the application of the definition gives you most of these results. For integers a, b, c, where a is non-zero, we have if a divides b and at the same time a divides c, then a divides b plus c. Okay, so if a divides b and also c, a also divides their sum, b plus c, and a also divides their product, b times c in this case. And finally, now the condition here is different. Uh, if a divides b and b divides c, then you get a divides c. So this is sort of the transitivity property for divisibility relation, let's say. Okay, so if a divides b in the second one, you don't need the second condition. A divides b and a divides c um, results in a divides b c. But of course, one of these is sufficient. If a divides b or a divides c, then you get a divides bc. Now, a corollary, an immediate corollary of this theorem is that for integers a, b, c, m, and n, where again a is non-zero, if you have a divides b and a divides c, then this implies a divides a linear combination of b and c, m times b plus n times c. Of course, everything here is integer. Be careful about this so that the divisibility result holds. Now, based on this definition, we have the division theorem. You can see this as the definition of division operation on integers. Here, a and d are integers where d is non-zero, so we exclude division by zero here, obviously. And the theorem states that there are unique integers. Now, this is important, the uniqueness part. Unique integers q and r such that r is between 0 inclusive and the absolute value of d exclusive, such that a equals d times q plus r. Now, the domain here is integers. It's not positive integers specifically, so negative values are allowed here. And be careful about this definition. And the most important aspect of this definition is this. Well, uniqueness is important, but the heart of this theorem is here. The remainder is between 0 and the absolute value of d, and be careful about what is included and what is excluded. Now here, this defines the division of the number a into d. So we call a the dividend, the number which we divide, d the divisor, the number that divides the dividend, q is the quotient, you can call this the result also, and r is the remainder. Okay, so this is the general picture of integer division. The result is also going to be an integer. Okay, it's not like real division where you get 3 divided by 2, 1.5. That's not the case here. When you divide 3 by 2, you get 1 with a remainder of 1 when we talk about integer division. Okay, so well, actually we do not really write this as this, but we write this as 3 equals 2 times 1 plus 1. Okay, and sometimes we write this as Q as A division D. Of course, this is not the natural notation we use, but this is more common notation, and we are going to use it today extensively. The remainder R equals A mod D, okay, A modulo D. Now, as I said, this is a trivial result. You all know from primary school probably, but maybe what is confusing is when you have negative operations or negative operands rather. So obviously, for instance, 11 equals 3 times 3 plus 2. So when you divide 11 by 3, the quotient is 3 and the remainder is 2. This is trivial. But what if you divide minus 11 by 3? 3 times what here and what is the remainder? So obviously, what is confusing is it 3 here, or rather minus 3, or minus 4? Now, at this point, you have to remember this condition here, and the remainder have to be non-negative and in magnitude smaller than the divisor. Therefore, if you put minus 3 here, you need to have minus 2 here, which makes the remainder negative. So you don't put minus 3 here. This should be minus 4, and the remainder should be 1 plus 1. Okay, therefore, minus 11 divided by 3, you get minus 4, and the remainder is 1 plus 1. Similarly, for instance, if you divide 11 by minus 3, again, in this case, your quotient is not 3, which would make the remainder negative, but plus 4 plus 1 here. Therefore, again, 11 divided by minus 3, the quotient is plus 4, and 11 modulo minus 3 gives you plus 1. So the remainder will have to be a positive value due to this condition here.